Gold feels permanent because it barely changes, yet the atoms themselves were born in violent cosmic events. Some of the strongest evidence points toward collisions between objects scarcely wider than a major city. Those objects are neutron stars, the compressed remnants left behind after certain massive stars explode. Before asking how they can make gold, we first need to understand what kind of matter they contain. A normal star survives because gravity pulling inward is balanced by pressure generated deep inside the star. When a sufficiently massive stellar core runs out of usable nuclear fuel, that balance can suddenly fail. The collapsing core is crushed so strongly that electrons and protons are driven into neutron-rich matter. If the remnant avoids becoming a black hole, what remains can settle into a neutron star. A neutron star can hold more mass than the Sun inside a sphere only a few tens of kilometers across. Its surface gravity is therefore immense, and its interior reaches densities far beyond ordinary laboratory matter. Atoms cannot remain intact in the familiar sense under the pressure found throughout most of this object. The result is not a giant ball of normal neutrons packed together like identical marbles. Different layers may contain nuclei, free neutrons, protons, electrons, and forms of matter still under debate. Deep near the center, physicists do not yet know exactly how matter behaves at such extreme density. That uncertainty is summarized by something called the equation of state for ultra-dense nuclear matter. The equation of state links pressure, density, temperature, and composition under conditions we cannot reproduce completely on Earth. Different equations of state predict slightly different neutron star sizes, internal structures, and responses to tidal forces. Those differences become important when two neutron stars begin pulling violently on each other before a merger. A neutron star may appear almost perfectly calm from a great distance, but its existence is already extreme. Its matter is held together by gravity powerful enough to reshape how space and time behave around it. When two such objects orbit together, their motion becomes a laboratory for gravity in its strongest measurable regime. It also creates the conditions that may eventually release neutron-rich material into surrounding space. That material matters because building elements heavier than iron requires a very different pathway from ordinary stellar fusion. Fusion releases energy efficiently while producing nuclei up through the iron region, but the process changes beyond there. To reach many much heavier nuclei, nature needs environments where atomic nuclei can capture large numbers of neutrons. One important route is the rapid neutron capture process, usually shortened to the R process. The R process requires extremely neutron-rich conditions and acts faster than many unstable nuclei can radioactively decay. Neutron stars are therefore compelling candidates because neutrons are already central to the matter inside them. But the material buried inside a neutron star cannot make observable gold simply by remaining trapped there. Something must first tear neutron-rich matter free, decompress it, heat it, and send it outward. A collision between two neutron stars can provide exactly that kind of disruption. Such collisions begin long before the stars physically touch, while the pair is still locked in orbit. Binary neutron stars usually descend from systems that once contained two massive ordinary stars. Each star must survive a complicated history of mass transfer, stellar evolution, and at least one supernova. If the system remains gravitationally bound after both remnants form, two neutron stars can continue circling together. At first, their separation may be large enough that the final merger lies millions or billions of years ahead, yet the orbit is not perfectly stable because accelerating masses disturb the geometry of space-time. According to general relativity, changing mass distributions can produce gravitational waves that propagate outward. These waves are not sound traveling through space, and they do not require any material medium. They are propagating distortions in space-time itself, carrying energy away from the orbiting system. That lost energy has a consequence that seems almost invisible at first. The neutron stars can no longer remain at exactly the same orbital separation. Their orbit slowly shrinks, and the two objects begin an inward spiral called an inspiral. As the separation decreases, the stars move faster and release gravitational wave energy at an increasing rate. This creates a feedback process in which energy loss makes the orbit tighter, and a tighter orbit loses energy faster. For most of the binary's lifetime, that inward motion can be extraordinarily slow. Near the end, however, the same process becomes dramatically faster as the stars race around each other. The final seconds, therefore, contain a compressed record of increasingly strong gravity and increasingly rapid orbital motion. Gravitational wave detectors do not photograph the two neutron stars or watch them as visible points of light. Instead, they measure tiny changes in distance caused as a passing gravitational wave stretches and squeezes space. The signal's evolving pattern contains information about the orbital motion that generated those distortions. As the stars spiral inward, the characteristic gravitational wave frequency rises because the orbital frequency is increasing. The signal also grows stronger as the system enters its final, most energetic phase. Together, that rising pitch and amplitude produce the familiar gravitational wave pattern known as a chirp. The word sounds simple, but the physics encoded in the chirp is remarkably rich. The rate at which the frequency changes depends strongly on the masses of the two orbiting objects. Relativistic waveform models can therefore infer combinations of the component masses from the observed gravitational wave pattern. Those inferred quantities are not obtained by placing the stars on a scale somewhere in space. They come from comparing measured data with theoretical predictions for how different binary systems should distort spacetime. That distinction between measurement and model-dependent inference will matter throughout the story of cosmic gold. On August 17, 2017, gravitational wave observatories recorded a signal, later designated GW170817. Its long inspiral signal was consistent with a binary containing compact objects in the neutron star mass range. The event became the central observed case linking gravitational waves from a neutron star merger with electromagnetic radiation. That combination would later transform the evidence for heavy element production, but the first message came through gravity. The gravitational wave signal directly recorded the changing strain produced as the binary approached its final moments. Its waveform showed the accelerating inspiral expected when two compact masses radiate orbital energy through gravitational waves. Researchers then used relativistic models to estimate properties such as the system's masses and possible tidal effects. Those estimates depend on the waveform models and assumptions used to interpret the detector data. The difference is subtle but important because observations and interpretations do not always carry identical certainty. GW170817 gave scientists a measured signal, while theory translated that signal into a physical portrait of the binary. One especially interesting possibility is that the final orbit can reveal how easily each neutron star is deformed. A neutron star in a binary is pulled by its companion's gravity and develops a tidal distortion. How strongly it deforms depends partly on its radius and on the behavior of ultra-dense matter inside it. That response can slightly alter the gravitational wave phase during the late inspiral. In principle, measuring those changes allows gravitational waves to probe matter at densities inaccessible to ordinary experiments. In practice, the constraints remain statistical and depend on detector sensitivity in the chosen physical models. GW170817 improved our knowledge of neutron star structure, but it did not reveal a unique equation of state. Several families of dense matter models can remain compatible with the available measurements and astrophysical constraints. That uncertainty will later affect estimates of how much matter can be thrown outward during the collision. A larger or more deformable star may respond differently to tidal forces than a more compact one. The masses of the two stars also influence whether matter is stripped away, shock, heated, or swallowed rapidly. So the story of nucleosynthesis already depends on details hidden inside the gravitational wave signal. Another uncertainty concerns what happens immediately after the two neutron stars finally make contact. The merged object does not always have to follow exactly the same path from one event to another. Depending on total mass and dense matter physics, the remnant may collapse quickly or survive temporarily as a massive neutron star. That later fate changes the surrounding disk, neutrino environment, and possible channels through which material can escape. But before any of those outcomes unfold, the final in-spiral drives the stars into an increasingly violent tidal encounter. Their surfaces rush around the common center of mass at a significant fraction of the speed of light. The orbital period shrinks until the system can complete many revolutions in a tiny span of human time. At this stage, the distinction between orbital dynamics and stellar structure becomes increasingly difficult to separate. The stars are no longer behaving like simple point masses that can ignore each other's physical size. Tidal forces begin stretching their outer layers while the orbital frequency continues climbing. At the same time, the gravitational wave signal is approaching the region where subtle matter effects become most important. What happens next determines how much neutron-rich material can escape instead of remaining trapped in the remnant. That escaping material will later become the raw environment in which the R process may operate. The eventual abundance of gold therefore begins with a gravitational problem before it becomes a nuclear one. Gravity determines the in-spiral, tidal forces reshape the stars, and the collision decides which material is released. Only after that release can nuclear reactions transform the rapidly changing debris into a new population of heavy nuclei. This is why gravitational waves and heavy element astronomy belong inside the same physical story. The waves tell us how the compact objects moved before the collision, while later light reveals what escaped afterward. GW 170817 became extraordinary because those different messengers could eventually be connected to the same cosmic event, yet at the end of the in-spiral alone, the future chemical outcome is still not directly visible. The neutron stars are almost touching, their outer layers are distorted, and space-time is carrying away enormous orbital energy. The next milliseconds will decide whether matter is torn outward, shock-heated, trapped, or drawn toward a newborn compact remnant. The stars have reached the edge of contact, and the question now becomes what the merger does to neutron-rich matter. At contact, the slow astronomical history of the binary collapses into a few milliseconds of extreme fluid motion. The stars are no longer separate compact spheres following clean orbits around a shared center. Their outer layers collide, shear past one another, and respond to enormous pressure gradients and tidal forces. What follows determines which pieces of neutron-rich matter remain trapped and which escape into space. Some material can be pulled outward by tidal forces before the merged object fully settles. Other material is compressed and shock-heated where the two stellar surfaces crash together. These two routes can produce ejecta with different temperatures, speeds, and proportions of neutrons and protons. That difference in composition will later influence which heavy nuclei the expanding debris can build. The collision does not simply explode two intact neutron stars into identical fragments. Instead, gravity, pressure, rotation, shocks, magnetic fields, and neutrinos begin influencing the remnant at once. The result is a rapidly changing system whose structure can differ substantially from one merger to another. The total mass and the behavior of ultra-dense matter help determine what kind of remnant forms. In some mergers, the combined object may collapse into a black hole very quickly. In others, a massive neutron star remnant can survive temporarily before possibly collapsing later. The exact dividing line depends partly on the still uncertain equation of state of dense nuclear matter. That uncertainty connects the unknown physics inside neutron stars directly to the amount of matter available for nucleosynthesis. A prompt collapse can pull much of the surrounding matter toward the newly formed black hole. A longer-lived remnant can continue heating, irradiating, and stirring the material around it. Both outcomes can leave behind a dense disk of hot material orbiting the central remnant. That disk becomes another possible source of matter that can later escape as slower outflows. Astrophysicists therefore describe merger ejecta as several overlapping components rather than one uniform cloud. Dynamical ejecta are expelled during the violent merger itself through tidal forces and shocks. Disk outflows emerge later as the surrounding torus evolves and loses material. Additional winds may be shaped by neutrino heating, magnetic processes, and the lifetime of the central remnant. These components matter because neutron richness is not simply determined by whether material came from a neutron star. High temperatures can break nuclei apart, while weak interactions can convert neutrons and protons into one another. Neutrinos streaming through the debris can also influence the final balance between neutrons and protons. Physicists often summarize that balance with a quantity called the electron fraction. A lower electron fraction generally corresponds to matter containing a larger proportion of neutrons. Very neutron-rich ejecta can drive the R process towards some of the heaviest nuclei found in nature. Material with more protons may instead favor a different mixture of lighter R process products. This is one reason a single merger can produce chemically different ejecta in different directions. As the expelled material expands, its density falls dramatically, and the nuclear environment changes almost immediately. Free neutrons remain abundant enough in some regions for seed nuclei to capture them at extraordinary rates. This is the rapid neutron capture process introduced earlier, now unfolding inside actual merger debris. The captures can occur faster than many unstable nuclei have time to undergo radioactive beta decay. A seed nucleus can therefore acquire neutron after neutron and move far from the stable nuclei familiar on Earth. These temporary nuclei can be extremely neutron-rich and may survive for only brief periods. As neutron captures slow, beta decays gradually convert some neutrons into protons inside the nuclei. That process moves the nuclear population back toward more stable combinations of protons and neutrons. Under sufficiently neutron-rich conditions, the reaction flow can reach nuclei heavier than gold and even the actinides. Some extremely heavy nuclei may undergo fission, splitting into smaller fragments that can re-enter the reaction network. This recycling can influence the final abundance pattern produced by the most neutron-rich ejecta. Exactly how strongly it matters depends on nuclear properties that remain difficult to measure directly. Many nuclei encountered along the R process path are so unstable that they do not naturally persist on Earth. Their masses, decay rates, neutron capture probabilities, and fission behavior must often be predicted theoretically. Different nuclear models can therefore predict somewhat different final quantities of individual heavy elements. The uncertainty begins at nuclear scales. It eventually affects estimates of chemical production across entire galaxies. Gold sits within this broader family of heavy nuclei rather than occupying a unique pathway of its own. The merger does not contain a special mechanism that notices gold and manufactures that element alone. Instead, the R process creates a distribution of nuclei shaped by neutron supply, temperature, expansion, and nuclear physics. Gold emerges as one recognizable member of that much larger pattern of newly assembled heavy matter. This distinction matters whenever a merger is described as producing a certain amount of gold. Models may estimate a total mass of R process ejecta more securely than the mass of one particular element. Converting that total into a gold yield requires assumptions about the final abundance pattern, so a memorable gold estimate can be scientifically useful while still carrying substantial model dependence. GW170817 gave astronomers a rare opportunity to test this entire picture against a real neutron star merger. The gravitational waves established the compact binary in spiral and merger as the source of the initial signal. A short gamma-ray burst was observed shortly afterward from the same general region of the sky. Optical and infrared observations then revealed a rapidly changing transient associated with the same event. Those observations confirmed that the merger was accompanied by luminous matter outside the final compact remnant. They did not directly weigh every gram of ejecta or identify every nucleus created in the collision. Instead, scientists compared the changing radiation with models of expanding, radioactively heated merger debris. That comparison produced strong evidence for substantial heavy element nucleosynthesis while leaving important quantitative uncertainties. One source of uncertainty is how much material escaped through each of the different ejecta channels. Tidal debris, shock-heated matter, and disk outflows can overlap in velocity and composition. Different simulations can assign somewhat different fractions of the observed emission to those components. The resulting uncertainty propagates into estimates of the total R process mass produced by the event. Another uncertainty concerns how long the central remnants survive before settling into its final state. A longer-lived neutron star remnant could alter surrounding matter through additional neutrino exposure and rotational energy. A rapid collapse to a black hole would change those conditions, and the evolution of the disk, GW 170817, constrained several possibilities, but it did not provide an uncontested stopwatch for the remnant's lifetime. That distinction is important because remnant history changes both the amount and composition of the escaping matter. The nucleosynthesis is therefore not controlled by one variable, but by a chain of linked physical conditions. Masses affect the merger, dense matter physics affects the remnant, and the remnant affects the ejecta. The ejecta then determine the neutron environment that controls the final R process abundance pattern. Even after the rapid neutron captures end, the newly created nuclei are far from finished evolving. Many are unstable and continue undergoing beta decay as the expanding cloud moves away from the merger. Some decay chains release particles and radiation while gradually approaching longer-lived or stable nuclei. Fission and other radioactive processes can contribute additional energy during this continuing nuclear evolution. This radioactive energy does something crucial for astronomers because it heats the expanding debris. Without that heating, much of the freshly synthesized material would remain nearly invisible at cosmological distances. Instead, part of the decay energy is converted into thermal radiation as the ejecta expand and cool. That radiation becomes the observable phenomenon known as a kilonova. A kilonova is not simply the visible flash produced at the instant two neutron stars collide. Its continuing glow is powered largely by radioactive decay within the expanding merger ejecta. The brightness, therefore, carries information about how much material was expelled and how quickly energy escapes. Its changing color carries additional information about the opacity and composition of that material. Opacity describes how difficult it is for radiation to travel through the expanding cloud. Some heavy elements, especially the lanthanide group, can create extremely complex patterns of atomic absorption. That complexity can make lanthanide-rich ejecta much more opaque than material containing lighter R-process nuclei. Higher opacity changes how rapidly the radiation escapes and shifts the emission toward longer wavelengths. This means the merger's chemistry can influence not only what exists in the debris, but how the debris looks. The connection is powerful, but it is not a simple one-to-one translation from color to element. Temperature, velocity, geometry, opacity, and radioactive heating all influence the light reaching a telescope. Extracting composition, therefore, requires models that combine nuclear physics, atomic physics, radiation transport, and hydrodynamics. GW 170817 provided exactly the kind of changing light needed to test these linked ideas. Its optical emission evolved rapidly, while substantial radiation later emerged more strongly at infrared wavelengths. That behavior was broadly consistent with expanding ejecta containing R-process material with different opacity properties. But turning that agreement into exact masses of individual elements requires additional assumptions and detailed modeling. The collision has now become something astronomers can study not only through gravity but through changing light. The R process has assembled unstable heavy nuclei, and their radioactive decay is heating the expanding debris. The chemistry is beginning to write itself into the brightness and color of the Kilonova. The next question is whether telescopes can read that light well enough to identify what the merger actually produced. To answer it, we have to follow the Kilonova as its light fades, reddens, and passes through a forest of atomic signatures. The merger has passed, but the most useful evidence is only beginning to emerge from the expanding debris. Freshly assembled nuclei are decaying, releasing energy into material racing away from the compact remnant. That energy produces a kilonova whose changing light can reveal clues about what the collision created. The challenge is separating what telescopes actually measure from what physical models infer from those measurements. The unstable nuclei formed by the R process contain stored nuclear energy that is released through radioactive decay. Decay products collide with surrounding matter and transfer some of their energy into the expanding cloud. The heated ejecta then radiate energy outward while simultaneously becoming larger, cooler, and more transparent. This competition between radioactive heating, expansion, and escaping radiation shapes the kilonova we observe. Astronomers track that evolution with a light curve, a record of brightness changing with time. A light curve tells us when the transient brightens, how luminous it becomes, and how quickly it fades. Observations through different filters also show whether the radiation shifts from bluer wavelengths toward redder ones. Those measurements are direct, but converting them into ejecta, mass, or composition requires additional physics. Radiation produced deep inside the ejecta cannot immediately escape if the surrounding material is highly opaque. Instead, photons interact repeatedly with matter before finally finding paths outward as the cloud expands. More ejecta generally gives radiation farther to travel, while greater opacity makes escape more difficult. Expansion speed also matters because faster material becomes diffuse and transparent on a different time scale. The optical counterpart of GW 170817 was initially bright and relatively blue before fading rapidly. That early blue emission indicated that at least some ejecta allowed visible radiation to escape comparatively quickly. Models can reproduce such behavior with rapidly expanding material containing relatively low amounts of lanthanides. That interpretation is physically motivated, but the observed color itself is the measurement, not the inferred composition. Over the following days, the transient faded in visible light, while becoming increasingly important at infrared wavelengths. The changing color was one of the clearest observational signatures that the ejecta were evolving rapidly. Models containing more opaque, heavy element-rich material naturally produce radiation that emerges later and at redder wavelengths. This made the red and infrared evolution an important clue to the presence of heavier R-process material. Lanthanides are especially important because their atomic structures contain enormous numbers of possible electron transitions. Those transitions can absorb and redistribute radiation across a dense forest of wavelengths. Even a modest amount of lanthanide-rich material can therefore change how rapidly energy leaves the ejecta. This atomic complexity is why chemistry can alter both the timing and color of a kilonova. A useful picture of GW 170817 often includes at least a bluer component and a redder component. The bluer material is commonly modeled as faster ejecta with lower opacity and fewer lanthanides. Redder emission is commonly associated with more opaque material containing a greater abundance of heavier R-process species, but these components are modeling tools, not photographs of neatly separated chemical shells. Light curves reveal when energy emerges, while spectroscopy asks a different question about how that light is distributed. A spectrum separates incoming radiation by wavelength, exposing broad features created as photons interact with atoms. Atomic species interact with particular ranges of wavelengths according to their internal electron structures. In principle, those interactions allow astronomers to connect spectral features with specific elements or groups of elements. A kilonova spectrum is much harder to read than the clean textbook pattern of a stationary laboratory gas. The ejecta expand at enormous speeds, causing spectral features from different regions to become broadened by motion. Many heavy elements also possess vast numbers of transitions that can overlap across the observed spectrum. The result can resemble a blended landscape rather than a row of isolated elemental fingerprints. GW 170817 was especially valuable because astronomers obtained detailed spectra while its kilonova was still rapidly evolving. Those spectra displayed broad structures that changed as the ejecta expanded, cooled, and became more transparent. The overall spectral behavior was consistent with material moving at a substantial fraction of light speed. It also gave researchers an opportunity to search for individual neutron capture elements inside the blended emission. A later reanalysis identified spectral features consistent with strontium in the ejecta from GW 170817. Strontium is a neutron capture element and can be produced within the broad family of our process reactions. Its identification provided a much more specific chemical connection than color evolution alone could provide. For the first time, a neutron capture element could be tied spectroscopically to this observed neutron-star merger. That result is important, but strontium is not gold and should not be treated as a direct gold detection. Strontium occupies a lighter region of the neutron capture abundance pattern than elements such as gold and platinum. Its presence confirms that neutron capture nucleosynthesis occurred, while heavier production requires broader spectral and light curve interpretation. The strength of the evidence therefore depends on exactly which chemical claim we are trying to make. Heavy element spectroscopy is further complicated because laboratory atomic data become less complete for many exotic ions. Researchers need accurate transition wavelengths and strengths before a theoretical spectrum can reliably match an observed one. Missing or uncertain atomic information can cause different compositions to produce surprisingly similar modeled spectra. This remains one reason that robust identification of individual heavy elements in kilonovae is difficult. Gold is particularly vulnerable to misunderstanding because it gives the story an irresistible human connection. A model can predict that conditions producing heavy R-process material should also create some elemental gold. That is different from observing a uniquely identifiable gold signature and directly weighing the gold in the ejecta. For GW 170817, the strongest conclusions concern broad R-process production rather than a precise measured gold mass. Light curves introduce another layer of inference because several physical parameters can change brightness in similar ways. Increasing ejecta mass can extend the diffusion time, but changing opacity can also delay escaping radiation. Different expansion velocities alter density evolution, while radioactive heating assumptions change the available energy. Several combinations can therefore reproduce parts of the same observed light curve. Researchers reduce those ambiguities by fitting many wavelengths and many observing times together rather than separately. Spectra provide additional constraints on velocity and opacity that brightness measurements alone cannot supply. Even then, inferred ejecta masses depend on assumptions about geometry, heating efficiency, and radiation transport. They should therefore be understood as physically constrained estimates rather than direct measurements on a scale. Geometry matters because merger ejecta are unlikely to expand as a perfectly uniform sphere. Different viewing angles can expose different combinations of fast, slow, lanthanide-poor, and lanthanide-rich material. The observed spectrum can therefore depend partly on where an observer sits relative to the merger axis. Radiation transfer models must account for that geometry when translating light into physical ejecta properties. Infrared observations become especially useful as the ejecta cool and the dominant radiation shifts to longer wavelengths. Late emission can probe material that was difficult to see during the bright early optical phase. For GW 170817, observations extending into the infrared strengthen the case for production beyond only the lightest R-process nuclei, but the precise contribution of individual isotopes to that late emission remains dependent on nuclear and atomic modeling. The radioactive heating rate itself is not supplied by one isotope dominating at every moment. Many unstable nuclei decay on different time scales, collectively feeding energy into the expanding ejecta. The predicted heating, therefore, depends on the abundance pattern produced by the underlying nuclear reaction network. Uncertain properties of exotic nuclei can propagate from microscopic calculations into modeled kilonova brightness. This is why total R-process ejecta and elemental gold must remain separate quantities throughout the analysis. A Kilonova model may constrain how much neutron-rich material was expelled within a plausible range. Estimating how much of that material ultimately became gold requires an assumed or calculated abundance distribution. The second number therefore carries uncertainties that the first number does not contain in exactly the same way. The power of GW 170817 came from combining evidence rather than expecting a single observation to answer everything. Gravitational waves traced the compact binary and spiral and tied the event to neutron star scale objects. Optical and infrared observations revealed rapidly evolving material outside the remnant, consistent with a radioactive kilonova. Spectroscopy then added chemical information that brightness and gravitational waves could not provide alone. The measured facts include the gravitational wave signal and the transients observed brightness, colors, and spectra. They also include the rapid evolution of that electromagnetic emission across several wavelength bands. The spectroscopic evidence for strontium adds a specific neutron capture element to that observational picture. Together, those measurements strongly establish that this neutron star merger produced neutron capture material and a kilonova. The inferred quantities include ejecta masses, component compositions, electron fractions, and the abundance of lanthanide-rich matter. They also include estimates for the total mass of R-process material synthesized during the event. Those conclusions can be strongly constrained without becoming completely independent of kilonova and nuclear models. Any exact elemental gold yield belongs even farther toward the model-dependent side of that chain. Important uncertainties remain in atomic line data, nuclear reaction properties, ejecta geometry, and radiation transport. The event also cannot tell us by itself how diverse neutron-star mergers are across the universe. Different masses, spins, equations of state, and remnant lifetimes may produce different ejecta and abundance patterns. One beautifully observed kilonova therefore establishes a physical possibility far better than it establishes a universal average. We now know that neutron-star mergers can create neutron capture elements and eject substantial heavy element-rich material. What remains uncertain is how often the relevant mergers occur and how much each one contributes over cosmic time. That is the step required before an observed kilonova can become part of an explanation for the galaxy's gold. The evidence from GW 170817 is powerful, but the cosmic inventory requires more than proving that the factory can operate. The final question is, how much of the universe's gold neutron star mergers can actually account for? GW 170817 showed that a neutron star merger can produce neutron capture material, but a cosmic inventory asks a much larger question. To explain the gold distributed through galaxies, we need more than evidence that one astrophysical factory can operate. We also need to know how much that factory produces, how often it runs, and when it began contributing. Each step adds another layer of inference between an observed merger and the history of heavy elements. The first quantity is the amount of R process material expelled by a typical neutron star merger. Kilonova observations can constrain that ejecta mass, but the answer depends on opacity, heating, geometry, and radiation models. Different binary masses and remnant outcomes can also change the amount and composition of material that escapes. So even an excellent estimate for GW170817 should not automatically become the yield assigned to every merger. The second quantity is the merger rate, meaning how frequently neutron star binaries actually collide across a given volume of space. Gravitational wave detections provide direct evidence that such mergers occur in the nearby universe, but converting a limited number of detections into a cosmic rate requires accounting for detector sensitivity and selection effects. The resulting rate is therefore a statistically inferred population quantity rather than something measured from one event alone. A detector is more likely to notice some binaries than others because signal strength depends on distance and orientation. Periods of observing downtime and changes in sensitivity further affect how many mergers enter the detected sample. Population analyses correct for these effects, but the inferred merger rate still carries a substantial statistical range. That uncertainty matters because cosmic production roughly depends on both yield per event and number of events. A rare event producing enormous amounts of heavy material can compete with a more common event producing less each time. This trade-off is central whenever astronomers compare different possible sources of the R process. Knowing a source is capable of producing heavy nuclei does not tell us whether it dominates the total inventory. Dominance depends on how productivity and frequency combine throughout the history of galaxies. Time introduces a third complication because neutron star mergers do not necessarily occur soon after their progenitor stars are born. A massive binary must first evolve through stellar collapse before two neutron stars can exist. The surviving compact binary can then spend additional time losing orbital energy before the final collision. That interval between stellar formation and merger is called a delay time. Different binaries can have very different delay times because their initial separations and evolutionary histories are not identical. Some systems can merge comparatively quickly, while others may orbit for billions of years before colliding. The distribution of those delays determines how efficiently mergers can enrich very young galaxies with our process material. This is where observations of ancient stars become part of the same story as gravitational wave astronomy. Some very old, metal-poor stars contain substantial amounts of our process elements despite forming early in galactic history. Those stellar abundances are measured from spectra and preserve information about the chemical environment from which the stars formed. Interpreting their history requires models of star formation, gas mixing, stellar evolution, and the timing of enrichment events. The observation is early enrichment, while the identity and timing of the source remain an astrophysical inference. Neutron star mergers can contribute early enough if some binaries merge on sufficiently short delay times. How common those rapid mergers were in the young universe remains an important uncertainty in chemical evolution models. Galactic gas also mixes imperfectly, so a single prolific event can enrich one region much more strongly than another. That uneven mixing can make early abundance patterns look more complicated than a simple galaxy-wide average. Small galaxies provide especially useful laboratories because a limited number of enrichment events can leave unusually clear chemical signatures. Some systems contain stars with striking R process enhancement, showing that rare events can sometimes deliver large heavy element yields. Those patterns are compatible with prolific sources such as compact object mergers, but chemistry alone does not identify every event uniquely. Chemical archaeology, therefore, constrains the population history without supplying a photograph of the original explosion. This leaves room for additional R-process sites that may contribute alongside neutron star mergers. One proposed class involves unusually energetic core collapse explosions shaped by rapid rotation and powerful magnetic fields. Another proposed environment is a collapsar, where a massive stellar core forms a black hole surrounded by an accretion disk. Under suitable conditions, outflows from such systems may also become neutron-rich enough for substantial R-process nucleosynthesis. The existence of alternatives does not weaken the evidence that neutron-star mergers produce heavy R-process material. It changes a different question, which is how the total cosmic contribution should be divided among possible sources. That division depends on each source's frequency, yield, delay time, environment, and evolution across cosmic history. Current observations do not reduce all of those quantities to a single uncontested answer. The same caution applies when translating total R-process production into a statement specifically about elemental gold. A merger may eject a certain total mass of neutron capture material according to a Kilonova model. Determining what fraction becomes gold requires a nuclear abundance calculation that introduces additional assumptions. Multiplying that gold yield by a cosmic merger rate adds population uncertainty on top of the nuclear uncertainty. A final comparison with stellar abundances then requires a model for how galaxies form, mix, and lose their gas. Each stage is scientifically useful, but none should be mistaken for a direct weighing of all gold in the universe. This layered uncertainty explains why different studies can reach different quantitative estimates without contradicting the basic merger evidence. The robust conclusion is narrower than the most dramatic headlines, but it is also more informative. Neutron-star mergers are established astrophysical sites where conditions can produce a broad range of neutron capture elements. GW170817 connected that nucleosynthesis to an independently detected compact binary merger through multiple kinds of astronomical evidence. That makes neutron-star mergers a major candidate for explaining a substantial fraction of cosmic R-process material. It does not establish that they supplied every R-process atom or every atom of gold. The special power of GW170817 came from observing the same event through physical messengers that respond to different processes. Gravitational waves trace the changing orbital dynamics of the compact binary before and during merger. A short gamma-ray burst provided evidence for a high-energy relativistic outflow associated with the event. Optical and infrared radiation tracked the expanding, cooling material outside the central remnant. Spectra added information about velocities, opacity, and the chemical species interacting with that light. Later emission at other wavelengths helped reveal how energy continued moving through the merger environment. No single messenger carried the entire explanation, and that limitation became a strength when the observations were combined. This method is known as multi-messenger astronomy because different signals reveal different parts of the same physical event. Multi-messenger evidence can establish associations that would remain ambiguous if only one channel were available. For GW170817, the gravitational wave signal identified the compact merger, while the Kilonova revealed luminous ejecta. The electromagnetic evolution then supplied information needed to test whether radioactive neutron capture material could explain that ejecta. The agreement across those channels is why the case for merger-driven heavy element nucleosynthesis became so strong. Yet, multi-messenger astronomy does not eliminate the need for models because each observation still requires physical interpretation. A gravitational wave waveform constrains masses and tidal properties through relativistic templates rather than direct imaging. A Kilonova light curve constrains ejecta properties through radiation models rather than direct collection of the debris. A spectrum constrains composition through atomic transitions whose interpretation can depend on incomplete atomic data. The value of combining messengers is that those different models must remain compatible with the same physical event. A proposed explanation that fits the light but contradicts the merger dynamics becomes harder to sustain. Likewise, a merger model that cannot produce ejecta compatible with the observed Kilonova faces an additional test. Several independent constraints can therefore narrow the allowed physical picture even when none is perfect alone. What remains unresolved is largely a population problem rather than a question of whether the basic mechanism exists. Astronomers need to understand how yields vary across many mergers rather than treating GW170817 as a universal template. They also need tighter merger rates and better knowledge of how those rates changed over cosmic time. Nuclear experiments and calculations must improve the properties of unstable nuclei that shape predicted abundance patterns. Atomic calculations must also improve the spectral fingerprints used to identify heavy species in expanding kilonova ejecta. Chemical evolution models then have to connect those event-scale results with billions of years of galactic history. Alternative R-process sites must be tested by the same accounting of yields, rates, timing, and observed chemical patterns. Only then can the relative contribution of each channel be estimated without assuming the answer in advance. The question of cosmic gold is therefore no longer whether neutron star mergers matter, but precisely how much they matter.
The deeper lesson here is not that one spectacular merger solved the history of gold. Its real strength is that several independent messengers forced different pieces of physics to confront the same event. Gravity described the motion, while the changing light tested what escaped and how that material evolved. That combination narrows the space for explanations without pretending that every remaining uncertainty has disappeared. The most useful conclusion is therefore proportional to the evidence, strong where measurements converge and cautious where models still carry the weight. That balance is what makes this event scientifically durable.
Returning to the observations, GW170817 established a benchmark rather than a final census of heavy element production. It demonstrated that neutron star mergers can unite strong gravity, relativistic outflows, radioactive ejecta, and neutron capture chemistry in one event. Future populations of well-observed mergers can reveal how often that combination produces similar or very different chemical outcomes. Until that population is better known, the total contribution to cosmic gold remains a constrained but model-dependent quantity. What is secure is that the merger process can release neutron-rich matter and build heavy nuclei through the R process. What remains uncertain is the exact share of the galactic and cosmic inventory supplied by this channel. Other rare stellar catastrophes may have contributed alongside mergers, especially in environments and epochs we cannot observe directly. So the gold story ends not with a single factory, but with a measurable network of cosmic processes still being untangled. When neutron stars collide, some of their compressed matter can escape, transform through nuclear decay, and disperse into interstellar space. Long after the ripples fade, those heavy atoms can remain, quietly joining the material from which future stars and worlds are made.